seconds.
Hey everyone, Michael Unger here from the H.R. McMillan Space Center, and this is our bonus coverage for Cosmic Night's black holes. And we have a very special guest all the way from the other side of the country in McGill University, Montreal, and that is Daryl Haggard. Hi, Daryl.
Hi, how's it going?
So in this little compendium, we're going to get into this amazing project that happened last year where astronomers took a picture of a black hole, which I thought was impossible. We're going to get into it. But first of all, Daryl, maybe tell us a bit about your research at McGill and how you got involved in the Event Horizon Telescope project.
Yeah, for sure. So I'm a professor at McGill University, and I have this amazing research group of about 10 grad students and postdocs and undergrads that work with me. And all of us study black holes and neutron stars and sometimes white dwarfs. And those things are called compact objects. So these are things that are really, really, really dense compositions that are extremely unusual, very hard to make here on Earth. So these are our astrophysical laboratories for how you build really dense objects in space. And black holes are for sure the most sort of exotic, and they've captured our imagination in a really cool way. So we work on black holes a lot in my research group. And in particular, my inroad into the Event Horizon Telescope collaboration is through this one specific supermassive black hole. So let me just quickly tell you, probably your other astronomers will tell people, but there are two kinds of black holes. There are little ones and there are big ones. The little ones we measure their mass in the same units as our sun. So they might be 10 times more massive than our sun. We call those solar units. The big ones are called supermassive black holes, and they can be millions to billions of times the mass of our sun. So my very favorite black hole is a supermassive black hole, and it's the one that lives right down in the center of the Milky Way galaxy, right here in our home galaxy, and it has a special name. It's called Sagittarius A star. So that sounds kind of funny, but if you look out in the night sky and you look in the direction of the constellation Sagittarius, you're actually looking toward the center of our Milky Way galaxy and toward this supermassive black hole that lives here in our galaxy. And so Sagittarius A star has been one of my very, very coolest research projects for probably going on 10 years now. And it happens to be one of only two supermassive black holes that the Event Horizon Telescope can take a picture of this hot material just outside the event horizon. And that's what gives us this amazing image of a black hole. So you're seeing all the photons just before they're captured by the black hole. And we can only take that kind of picture for two black holes. One is Sagittarius A star, and the other one is called M87. And that's the one that you guys have seen the picture of. Okay. And so I work on both of those sources, but you've only really gotten the sneak preview of the M87 black hole.
Oh, wow. So this is exciting. So the next picture that's going to come out is going to be a picture of our black hole. Can we call it our black hole?
Yeah, I call it our black hole.
Well,
it's my very best friend, supermassive black hole. It can be yours too.
Well, tell us a little bit about this, because this is a very unique telescope. Maybe tell us a little bit about how the Event Horizon Telescope works.
Yeah, so the Event Horizon Telescope is very unique. It's using a technique that's actually been developed for many years by long wavelength astronomers, so people that work at radio and sub-millimeter wavelengths. And this is called very long baseline interferometry, which is a fancy way of saying if you have two telescopes that are very far apart, you can actually link them together and make them act like one telescope. And so that's the underlying premise of the Event Horizon Telescope. We've actually placed telescopes all over the globe, across the whole Earth, and we link them together so that they can operate as if they are a single telescope. So here's a kind of a weird analogy, but it looks a little bit like this. When you think of a telescope, normally you think of this huge glass mirror. That's normally the picture we have in our minds. Mm-hmm. So imagine now that that glass mirror is like the size of our globe, and it's mostly empty, and you only have tiny little shiny patches, tiny little collecting places at the positions of each of these telescopes around the globe. So it's a very imperfect telescope. It's missing a lot of the collecting area, but it's really big. And the fact that it's so big actually lets you go in there and see structures that are super tiny. And that's what you need when you want to see a black hole, because black holes, I was telling you before, they're super dense. And that means that they're also really, really small. So the trick of the Event Horizon Telescope is that we don't have that much collecting area, but we've got a huge surface. And that huge surface lets us get in there and see that teeny, teeny little resolution that you need to see the event horizon of the black hole.
Awesome. So this this new picture that you're taking of the black hole, is that in the middle of that process right now?
You mean Sagittarius A
Yeah.
star? Yeah, so every season when we go out and observe, we actually observe many black holes, not only these two. So M87 and Sagittarius A star get observed every year we go out to observe. But M87 is a more massive black hole, and it's a little bit more stable. So all the stuff around it doesn't move quite so quickly. So it's easier when you're learning how to use this new instrument to take the very massive, very static image and share that with everyone. So that's what you've seen already, and that's what generated all this excitement. It's really amazing. And M87, just so that I don't give it any short shrift, is a super cool black hole. And M87, one of the things it has is this incredibly bright jet. It's got this really energetic jet flying out of the center of the black hole. And so that's really awesome. M87 is cool. But Sag A star is 2 orders of magnitude smaller. So it's only a million times the mass of our sun. And partly because it's smaller than M87, less massive, it varies much more quickly. So it changes actually on the time scale of a night while we're trying to look at it. And you can imagine the difference between photographers learning how to take a static picture versus piecing together a bunch of images to make a movie or a video. So first we started with a static picture of M87, and now what we have to learn how to do is to put all these very quickly changing images of Sagittarius A star together to give you actually something that varies over the course of a couple of hours. So that's the reason we haven't shared it with you yet. You know, it's coming. I promise you, you all will see it sometime soon. But it's much, much more difficult for us to capture that clean black hole image. Right. And also the variability, which is going to be amazing and awesome, just makes the image reconstruction, as we call it, more challenging.
Now, maybe tell us a bit about what these pictures are telling us about black holes that we didn't know before. What are some of the things that have surprised you in this process with the Event Horizon Telescope? Yeah,
so the Event Horizon Telescope images are really incredible. So don't forget that this is a tiny, tiny, tiny object very far away. It's very massive, and it contains material in a state that we cannot study in a laboratory here on Earth. It's too massive, it's too dense, and we can't recreate it in our laboratories. So we're left with looking at the kind of large scale surrounds around the black hole and simulating what we think it might do using things like general relativity and magnetohydrodynamics, you know, lots of fancy theories to try to understand what we think might happen. But this is the first time you can get really down in close there and look, okay, so are our theories of general relativity correct? And now if I stick a magnetic field in there amongst the material, what happens? Do I actually understand those physics? And this is our probe, our ability to walk down really close to that black hole and see those theories at work and see whether we've got them right. So that's kind of what we're trying to do with these images. As far as things that we didn't expect, so far M87 has showed us a lot of things that we did expect. So it's been a beautiful confirmation of general relativity to date. One thing that we still are working very hard to understand with M87 is that amazing jet I told you about. We really don't know how black holes make those things. And so as we get more sophisticated at imaging M87, we want to see, what is the magnetic field doing next to the black hole, and how does that generate this enormous jet that goes out for, you know, many hundreds and hundreds of times the radius of the galaxy that the black hole is buried in. So these are the sorts of things that we're trying to use the event horizon to tell us what's happening to the plasma, what's happening to the photons, and how are these different systems linked together, and do we get that physics yet, or do we need to come up with new physics to understand how it's working?
Wow, that's amazing. So really what this is helping us all understand is that question of what would happen to us if we got close to a black hole, because we always get those questions a lot where people come and we're talking about black holes because we're talking about the most powerful things in the universe. And this is really interesting. What you're saying is that it's helping us understand what is going on around that black hole because we still don't quite understand that fully, right?
Yeah, and you got to imagine it's not just what would happen to you and me, but really what even happens to little photons. I mean, black holes affect not just mass, but the photons themselves, right? They're really, really exotic and interesting objects. And so, yeah, these are amazing probes of how they impact their environment.
Amazing. Well, one of the questions, one of the fun surveys that we're doing with all of our attendees for our Black Holes event is, our black hole is called Sagittarius A star, but if you were to give it a new name, a new unique name, what would you call our Milky Way black hole?
Yeah, so that's a great question. The Milky Way black hole, ooh, what would I call it? I'm looking at your Black Sabbath album behind your head, so I have to admit that I'm a little bit biased by that. I also just watched the Bones Brigade skateboarding documentary recently, so I'm feeling like, gosh, that's a really high bar. I will say there's been a wonderful effort, and I won't try to trot on this territory, but people have come up with really amazing names from our First Nations communities. Oh, yeah. And so in particular, M87 does have a wonderful First Nations name, which I will probably misspeak. So let me see whether I can get the pronunciation. Powehī, but excuse me if I'm misstating that. Others of your audience can probably say it better than I can. But it has a beautiful definition as well. Powehī for the Hawaiian people is let me see if I can find, well, maybe I'll let you all look it up and share it with people. But it basically means sort of like the great unknown. Right. And so I think this is one of the great things about black holes is they are this great, massive, dark uncertainty, right? So maybe the dark uncertainty.
Wonderful. Before we let you go, Daryl, I'm very curious about you and how you got involved in astronomy in the first place, and what your connection is that made you want to dedicate your life to looking up at the stars.
Yeah, so I actually have a very weird background. I mean, there's ways in which, when you look back, things all seem like they were connected, but as you're going through them, they don't seem connected. I actually did my undergraduate education in philosophy, not in physics or astrophysics. And what I remember as being my origin story for being an astronomer was that we were studying Newton's Principia, like really the old book written by Newton. And one of the professors that was leading this discussion in my class was talking about how spacecraft engineers, they actually use the gravitational fields to do a gravitational assist with spacecraft to give them an extra boost to get them further out into the solar system. So when you look at these maps of spacecraft moving through our solar system, they actually ricochet off of the planets in our solar system. And I was just like, wow, that's awesome. That is what I want to study. And so that's how I remember it. But of course, when I won my very first big research grant, my mom sent me my junior high school poster from a junior high school poster competition. And it was what happens when galaxies collide. So she says that the origin was much earlier.
Oh, I love it. Do you ever get a chance to use your philosophy background in your studies now?
Oh, I think they're all very connected. Philosophy and astronomy, they're very old, and they were really just all the natural sciences originally. And so, yeah, absolutely. And in my philosophy program, we did actually study a lot of classic literature in the sciences. So that included Newton's Principia and Einstein's theory of relativity, at least the basics of it, and lots of Euclidean mathematics and calculus. So yes, absolutely, for sure, from that perspective. And also just an appreciation for reading and writing and how important that is for scientists. I think many of us don't know, but scientists read and write and write and write and write constantly. And so a lot of that training is used every day in my work.
Right. Well, Daryl, this has been a fascinating conversation. Thank you so much for taking time out of your day and joining us. And we'll see everyone back in the Black Holes event.
Bye, everyone.
10 seconds.